Okay, so we'll continue our discussion of mixed integer nonlinear optimization problems with non-convex expressions. And we looked at a broad outline of ways of creating outer approximations or underestimators and overestimators for non-convex expression. In particular, we saw the McCormick underestimators. And in this class, I'm going to tell you about a general framework for constructing these outer approximations or underestimators. And that's known as factorable forms. So this is a generic relaxation strategy. This will work for almost any functions. There's some exceptions, and I'll tell you what these, or at least give an example of some of these exceptions. And then I'll give an outline of the spatial branch and bound algorithm. So this is now a formal way of describing what I sort of scribbled on the board earlier, and then we'll talk about some takeaways in summary. So we're going to look at a general mixed integer nonlinear optimization problems that has functions f and g that are possibly non-convex in addition to, so we have non-convexity of functions in addition to the non-convexity of the integer variables. And we make one very important assumption here. We assume that the functions we're dealing with are factorable. And this term factorable means that we can express our function as the sum of products of unary functions of a finite set whose arguments are variables, constants, or other functions. I think there could also be sum or products of unary functions. This should be an or. So in particular, we're going to look at functions that are combinations of functions from a small set of operators. So when you code up your function in AMPL, GAMS, or Python, I'm going to assume that you're only using a finite alphabet of functional forms. And this would, for example, include all these operators here: addition, multiplication, division, exponentiation, sine, cosine, maybe allow you tangent, exponentiation, logarithm, maybe absolute values. What I'm not going to allow you to do is take functions that are, for example, integrals of other functions. Now, I could relax this if I knew how to form this integral analytically and get, again, a factorable function, then I could allow you to do this, but it's easier to do this. And in particular, I'm not allowing you to take functions that I can't see inside. So those are called black box functions, where you're not telling me what the functional forms are. And functions of this type can be expressed as an expression tree. And this expression tree plays a critical role both in the constructions of these underestimators that we're going to construct, but also, it turns out, there's another role for them in terms of automatic differentiation, how you get gradients for these functions. But I'm not going to talk about that here. So here is an expression tree. And there's a quiz that goes with the expression tree. I'm going to tell you how to read the expression tree. And while I'm telling you how to read it, you can try answering this question. So this is an expression tree for the function f of x1 and x2. And the question is, what is f of x1 and x2? So pretend this is a quiz show or something. So how do I read this expression tree? I actually start at the leaves, and the leaves are either variables or constants. And then I follow the sort of arrows backwards, and I perform the operation that I see here. So this is, for example, exponentiation of x2 with this constant 3. This would be taking the logarithm of x2, and here I would be multiplying whatever comes out of this, which is the logarithm of x2 with x1. So has anybody guessed who the function is? Yes, we have a winner. Okay, so let's write your answer down. Can you tell us again? x1 log x2 plus x2 cubed. Okay, let us see what the board reveals. So it's correct. Brilliant. Excellent. This decomposition is not unique. So there's other ways of writing it. Sometimes a cleaner way of writing it would be to actually have only one leaf node for x2, so that these two leaf nodes that I have here for x2 would actually be, I could have them coded as the same leaf node. But this is a very convenient way of writing down my nonlinear functions because it decomposes the function, it splits it up into its individual components. So now what I can do is I can look at, I have this expression here, and if I have a way of finding an underestimator for this function here, I'm minimizing, then I have part of my underestimator already constructed for my objective. And then here I have a bilinear term, so I know how to construct underestimators for bilinear terms, and then I just need to figure out what to do with the logarithm of x2. So it gives me a way of splitting the function up into very simple components, and I only need to study how to construct underestimators or outer approximation for these simpler components. So I don't need to do it for all possible functions, I just need to do it for this alphabet of possible functions that I have. Okay, so the way we then construct a relaxation is by using this computational graph. So in particular, we're also going to combine expression trees of the objective and the constraints. So we're going to write down what's maybe a forest of trees. We have an objective function and we have constraints. And for each of those, we also have associated bounds. So for example, for our inequality constraints, there's a lower bound of -infinity and an upper bound of 0 here. The leaf nodes of all trees are represented by variables, so the x or the y variables, the continuous or the integer variables. So and this gives us a directed acyclic graph, and all the modeling languages use this representation or some form of representation like this internally. So Ampel and GAMS have this directed acyclic graph and an API that allows you to interact with it, an API that allows you to traverse this graph, or you could even copy the graph and then construct a different graph that is potentially an underestimating graph. So here's a slightly more complex DAG. This is of an optimization problem. So now I have a nonlinear objective function, x1 plus x2 squared. So can somebody tell me which of these three functions up there is the objective function? Left, right, or the middle? Which one? The first one. Okay, correct. So the first one is x1 plus x2 squared. That goes in there. And then I have two more functions here, two more nonlinear functions. This second one is obviously this one here because it involves the sign. And then there's a function here that has a constant -5 that's being added. That's over there. And so the nodes that don't have any entering arcs are the objectives or the constraints, and I can construct my problem by writing it down in this way. Oh, so the graph doesn't show that, but I assume that I have bounds that are connected to each of my roots up here, if you like. So each of these will have bounds connected to it, and each of the variables will have, the leaves will also have bounds connected to it. So the two variables have bounds, and then up here I will have bounds. And so the bounds are, in a sense, separate from the representation of the graph. And so in our case, the bounds on the constraints are -infinity and 0. And on the objective is if we have an upper bound, then we put that upper bound, and otherwise it's -infinity as well, the lower bound. So the bounds are kind of separate from the graph structure. And that's good because it allows me more freedom if I want to have, if I had lower bounds, for example, or other expressions, equality constraints, then I might want to treat this differently. Okay, so now what I can now do is I have all my functions are expressed in terms of simple operations that are either things like multiplication of two variables, taking a sign, or exponentiating a variable, and then just some additions here. So all my functions are now expressed in terms of these very simple unary or binary operations. And that means that I can rewrite my whole mixed integer nonlinear optimization problem by sort of writing it in terms of a new problem in which I look at having these unary and binary operators that I'm operating with as I'm going through my tree. So to make this a little bit easier, I'm going to combine all my variables x and y just into a single x. So from now on, it's just going to be variables x. We're not going to separate out the integer variables, just because as far as this tree is concerned, it's much easier if you think of one vector of variables rather than carrying around the two. And so what I'm going to do is I'm going to introduce additional variables for each of the intermediate components in my directed acyclic graph that I'm computing. So each of these theta k is now one of the little functions that appears here. So there's a sign here, for example, an exponentiation or a multiplication of two variables. So each one of those becomes its own additional new variable. So I'm introducing additional variable now, and there could be quite a lot of these, one corresponding to each of these operator nodes in my tree. And then with these new variables, the operators are now these simple functions. So I had this alphabet of simple functions, and I'm making up more complex functions out of these simple functions. And each of these simple functions allows me now to get an outer approximation. So for example, for the multiplication of two variables, that's the McCormick envelope that we constructed. So we know whenever we see multiplication of two variables, we can replace this function that we have here. If this were a multiplication of two variables, but we can replace it by the McCormick envelope. And similarly, we have similar expressions for other functions. So I showed you some, for example, for a cube. I showed you an expression for the square. So you have to remember all of those. They're then coded up, and you will construct these outer approximations for these functions. And one additional point is that I also have bounds on my variables and even on the additional variables, and I'll tell you in the next lecture how to get these bounds. That's really important as well. Okay, so here's a simple example where I'm sort of reformulating my mixed integer nonlinear optimization problem in factorable form. And I've color-coded the different expressions here. So my variables are, and I don't think this is correct. So there's already a mistake here. So only x1 and x2 are integer variables. The remaining variables are not necessarily integers because they're results of nonlinear expressions. So that's actually a mistake. So I'll mark this up here. And then for each of my nonlinear terms that I find here, I introduce an additional variable. So here I've introduced x3 for sine x2. And then I have another term, this is now this inequality here. x4 is x1 plus x3 minus 4. That's this less than or equal inequality here. Yeah?
The right is correct, but it's derived from. So x3 and x4 are not integer because x3 is the sign of an integer variable. But everything else is the sum of the square root.
Right, yeah. So, that's right. So x3 and x4 are not in there. Yeah, no, you're right. Yeah. Okay, so it is correct, yeah. So you have to be careful to remember that not every operation, when you put an integer into it, gives you an integer. But somehow, when I copied this or derived this, I did the correct thing there. So this is actually important that we want as many constraints on these variables as possible. So thank you, Pietro. And then the second one, I introduce a variable x5 for my bilinear term and x6 for my cubed. And then I write this constraint. That's this constraint here, x7 plus is x5 plus x6 minus 5, less than or equal to 0. And then I have just one more nonlinear term, which is x2 squared, which I call x8. So I've introduced 3, 4, 5, 6, 7, 8. I've introduced 6 additional variables to do this. So this might look really complicated, But the reason I'm doing this is because now I only need to find underestimators, outer approximations for much simpler functions. So all my functions are going to look like, if I have a lot of x2 squared functions there, then I just do this underestimator once and I can apply it to all these functions. I don't need to have a library of very complicated functions for more complicated nonlinear expressions. Okay, and then we have the original bounds on x1 and x up there. This between 10. I was looking for the bounds down here. Oh, there's the bounds on x2. And so now I can use these bounds to derive bounds on x3 and x4, for example. So let's do that. So x3 is the sine of x2. So the sine, no matter what you stick in there, is going to be between -1 and 1. That's certainly valid. X4 is this expression here, and I'll just assume that I did the algebra right. Let's do x5 next. So it's x1 times x2. And x1 times x2, well, the lowest it can go is if I choose x1 to be -1 and x2 to be 4, then the product is -40. And if I choose x1 to be 4 and x2 to be 10, then I get the upper bound of 40. So that's a valid upper bound on these new variables. Let's do one more. x8 is x2 squared. So here's x8, and that's correct, right? If x2 is between 0 and 10, then x8 is between 0 and 100. And I wrote it there. Integrality is inherited from functions. So in particular, the sine x3 is not necessarily, if x1 and x2 are integers, then that's not necessarily an integer. And if x3 is not an integer, then of course x4 is not an integer. But all the other functions are now integers as well, because the square of an integer is integer, multiplying two integer gives you an integer, and the cube of an integer is integer. Okay, so everything is here is correct. This decomposition is not necessarily unique. And a simple example is that if you take the expression x1 times x2 times x3, then I can either write this as, I can multiply x1 with x2 and then multiply the result with x3, or I can do another one where I first multiply x1 with x3, and then I multiply the result with x2. And then I can do another one. So you can do many different ways of rewriting this. And if you have more complex expressions, then again, it's not unique, right? Do I first, if you think about having sine of x1 times cosine of x2 times x3, then there's different ways of doing that. And maybe there's different nonlinear functions that have different properties that might make one better than the other. But I've never looked into that, and I don't know if anybody has. Okay, so here's a little theorem that says the original problem and the problem that we rewrote during this really difficult, seemingly difficult and laborsome way of writing it as factorable function is equivalent. And of course it's equivalent. That's how we constructed it, right? We do the right math. So we did all this, and this problem that I've written down here, this optimization problem down here, is entirely equivalent to this problem up here. It's much bigger, it's got more variables, it looks daunting, but it's a much easier problem if you want to construct underestimators, because you don't need to do that for every time you have expressions such as these, which would be much harder to do outer approximations. And so now what I get is that I have these non-convex sets, which are rather simple non-convex sets. So I have little pieces of non-convex sets, and I write my original problem equivalently in this reformulated way. So previously I had I'd written my new variables, defined them in terms of expressions that are simple unary or binary expressions, and I can write that also equivalent in the set notation here. So I now have this set of this collection of non-convex sets, and the two problems are entirely equivalent. I just rewrote it, I made no mistake. And now the way to get convex relaxations is really easy, because now I just need to relax each of these individual sets. And so I do that by putting this little hash mark on top. I need to really, symbolically, I need to do this. And then I have a convex relaxation. So now if I have a function, x2 cubed, for example, that's a non-convex nonlinear function. Then I relax it by, for example, taking, I can take these two secants here and then joining them up. And so I can relax this constraint to the set that's now this convex relaxation. And so the critical part in this convex relaxation is that any feasible point, that's any point on the white line, is still in my convex relaxation. But the nice thing is that I now have a convex set. So I can minimize over this convex set, and then I'm going to, and this is sort of looking forward, I'm going to somehow separate this set and split it up and create my branch and bound tree. So in general, I get these convex relaxations, and I can do this. I know how to do this for all the functions. I can study these functions and find these convex relaxations. But really what I'm interested in is finding polyhedral relaxations. And so I'm assuming that, or I'm constructing myself a set of polyhedral relaxations that can just be written as a set of linear inequality constraints plus lower and upper bounds on all my variables. And notice that each of these sets are very small, so they're all only 1 or 2 dimensional sets. They're not going to have many variables, or 2 or 3 dimensional sets. They're not going to have many variables in them. So this is actually very efficient. I split my function, my problem up into these smaller boxes that I'm working with. And so I can construct these polyhedral sets for simple functions. So I've done it over here for the cubed. That's a polyhedral relaxation. I can do something similar for the McCormick or when I get the McCormick underestimators for the bilinear terms. And I can construct these sets and get a linear linear optimization relaxation of a mixed integer nonlinear optimization problem. And with that, I can now do branch and bound. And Smith and Pantelidis, I think, were the first to sort of realize that the connection to the computational graph, and that they could use this to actually create this whole mechanism automatically. And this is now standard in the optimization solver that we have. And so I'm going to describe this branch and bound routine. First of all, I'm going to need a procedure to compute lower bounds for my subproblems. And then I need to partition the feasible set. So I have a nonlinear optimization problem, which is nominally this non-convex problem here, but I'm going to relax that to a linear optimization subproblem. So this is a non-convex nonlinear optimization problem because it still has these equality constraints here, which I can relax to an affine feasible set. And so if I relax these inequalities to my affine feasible set, then I get a linear optimization problem on this node in the branch and bound tree that I can solve. And so what I do, the procedure is then basically going to be, I'm going to solve this linear optimization problem that is here. If the optimal solution is also, or if this linear optimization problem is infeasible, then I know that the original problem, of which this is a relaxation, is also infeasible. So I can prune this node. I don't need to look for solutions in that part of the branch and bound tree. Otherwise, I look at its solution, and if the solution is feasible in my nonlinear optimization problem, and hence in my mixed integer nonlinear version, then I have a new incumbent. And so whenever the solution of this polyhedral relaxation is feasible in the original nonlinear optimization problem, then it also solves the original nonlinear optimization problem because the objectives are the same. But generally, the solution of this problem will not be feasible in my nonlinear optimization problem, and then I need to branch. And so I can either then branch by picking a binary variable that's fractional and setting it to it's below its floor or above its ceiling. That's the standard mixed integer nonlinear branching. Or I can find myself a violated non-convex constraint and branch on that constraint. And so in this example here, if my solution to my relaxation were here at the red dot, then one way to branch would be to say I'm going to separate on this line here, and I'm going to create two new problems, one where my variable xi is less than or equal to this threshold, and one where it's greater or equal to the threshold. But that in itself is not enough. I also need to then refine this polyhedral relaxation. In particular, I need to separate. I want to eliminate this point from the solution of both of these subproblems that I'm creating. I'm now branching, and I got one problem over here and another problem over here. And so the way to separate then would be to say I'll construct myself a new polyhedral approximation. So I can do, for example, I can do this on the left. Oops. And then my new polyhedral approximation would be this one here, and this point is not feasible there. And on the right, I can do something similar. I can sort of add a cut here. I might also strengthen it, I should probably strengthen it to lie there as well. I should do the same here. And then I have these two feasible sets now. And so I now have two separate problems, two different problems. And what's critical is that the solution to the parent node is no longer feasible in either one of these. So in addition to branching, I need to do a little bit of extra work and refine this approximation that I'm having. And if I keep doing that, then you hopefully believe me that you get closer and closer to the nonlinear functions. Right? Once the sets become really small, so once my intervals on this axis become very small, then the polyhedral sets that approximate this function will look almost like the function, because the linearization gets tighter and tighter. And so this was the example that we looked on earlier, where we had this large, the non-convex feasible set is the dark black line. The polyhedral relaxation is the lighter gray area. We found this solution here, xi hat, xj hat. We found a branching point, and we found these two additional cuts that we can now use to separate into the problem on the right and the problem on the left. So very important that you add these cuts. Otherwise, the point remains potentially feasible in both these problems. And I had the slide earlier, so it's important to remember all the tricks we learned for mixed integer nonlinear optimization here. And the branching point plays an even more critical role here. So doing these tricks is even more important. And in addition, your branch and bound tree is more complex. You used to only branch on integer variables. Now you're branching on integer variables and these nonlinear expressions. And so there are more things to branch on, and the trees get larger. And so it's more important to choose your branching variables wisely. We want to minimize the size of this tree, ideally. Okay, so this is my last slide, and I'll go through this for this talk. So this is the branch and bound for non-convex mixed integer nonlinear optimization. And it's very similar to the branch and bound that we've seen earlier. You remove a nonlinear optimization problem from your heap. You initially put the relaxation, the continuous relaxation of the mixed integer nonlinear optimization problem on the heap. Then you solve a relaxation, so this gives you a lower bound, and you let this solution be XLU. And you can possibly get an upper bound too. So there's, if you want to, you can do this as well, and that could be useful. If this linearization is infeasible, then because we constructed this linearization to include the feasible set of the true nonlinear function, then we can prune this node. It's infeasible. We don't need to ever go back to this node. If the solution at this node is dominated by an upper bound that we've somehow constructed, then we can also prune this node because we already have a better solution. And otherwise, there are two things that we need to look at. Is the solution integer? Is it an integral value? And do we satisfy all of the nonlinear constraints that we have in the problem? And if both of these are true, then we found a new, better point. So we're now in this branch where we're no longer worse than what we had found before, so we can update our incumbent. We have a new best solution. And if neither of these are true, then we can either branch on a variable, so we can either find an integer variable which is non-integral and branch on it, or we can branch on one of these nonlinear expressions. So we can branch on a constraint that's not satisfied. So that's the two options that we have. And a lot of effort probably goes into finding out which one is the better way to do it, and that also might be problem dependent. And it depends on how the nonlinear expressions depend on your integer variables. Okay, so factorable programming. Factorable forms means that we have a generic way of constructing outer approximation, underestimators, or convex enclosures of our non-convex nonlinear feasible set. This will work as long as we take our functions and make them only out of the same simple building blocks. So this is a bit like Lego. You have the same building blocks and you build complex functions out of always using the same building blocks. Things like exponentiation, addition, sines, cosines, and so on. So this is a general recipe for constructing underestimators. And with that, I can then define a spatial branch and bound algorithm. And I no longer need to worry about every possible function that somebody could give me. I just need to worry about disentangling the nonlinear function that I get and constructing these individual underestimators. And that's the basis of all the successful global optimization solvers that are out there now. So like Pietro's Quen or Baron, for example. And with that, I'll be happy to answer some more questions. Any question? Yes. Oh, how do I add the affine constraints? Okay, let's go back. So I start off with this set here, which is, or this nonlinear constraint, which is a generic constraint. And now I say construct these affine sets. And I've really only told you for one particular function how to do it. And that's for the bilinear term. So I've only told you for, if you have a term xi times xj, we had the four McCormick underestimators, and those were the four functions that I showed you. For other functions, you basically have some recipe. So you would say for xi squared, you know that this function is convex, but if you have xk equals xi squared, then it's not convex. But you can take, you know that the secant, so one of your inequalities would be the secant that comes from the lower bound on Li and the upper bound, the lower bound on xi and the upper bound on xi. So that's one. You can do that. And now you can, depending on, it's your choice as an algorithm developer, you could set up a number of additional points at which you linearize the function. And you know that each of these linearization is an underestimator. So you could have, for example, a fixed number of these linearization points, like in this case 3, and then you would need to add these 3 cuts to it. So here there would be, I've constructed these 4 cuts here, And then in addition, I have the lower and the upper bounds. So that's how I construct this set. But I have to do it for this limited number of functions that I have in my alphabet. So let's see, where's my alphabet? Yeah, so that's right. So okay, I can do sine of x, then I can, I can look at where I am, right? I mean, so now this depends where I am. If my variable is if my bounds tell me I'm between 0 and pi, then I can use the fact that this guy is convex and I have a secant. And if I'm in the other one, concave and a secant, so I get those. And if I'm in the other region, then I need to do something else. If I'm spread over two regions, then I would again construct my underestimators. But it's really case by case. You can do it for each of these functions. You would figure out what a good way would be for you to construct them, and that's sort of coded in the code. Sorry? Correct. It's for each function, but it's only a small number of functions. I only have to do it for this small number of functions. So if I had another so this was sine x1. If I had an x2 squared here, then I would separate them out. Yes, I would always have to separate them out, and they're probably not as tight as possibly the combination of these two if you take them together. But you may be able to find tighter, not for the addition, I don't think for the addition, but for multiplication, for example, you could find maybe tighter relaxations. But you would find tighter relaxation, but you would need to have a much larger alphabet of functions for which you would have to do it. So if I instead took multiplication here, right, then I would separate this out. I would have, so this would be one function. So this is my bar, this is my theta 1 of x1, and this would be a different function, theta 2 of x2. And I would introduce new variables, x3, which is theta 1 of x1, x4, which is theta 2 of x2, and then I would write x5, which is x3 times x4. And so I have three sets of these outer approximations that I need to create. I create this one for x3, then I go over there for this one, and for the McCormick, I need to go back up there. But and you're right, if you study this function long enough, you can probably find something that is much tighter. But you have a much larger alphabet now for functions for which you have to provide underestimators. And so there's a trade-off between having code and functions that are easy to implement versus something that gets unwieldy. But having said that, I think all the Quen is extensible, so you could potentially write your own function in there if you wanted to. And guess what? If you have a stronger underestimator for this guy, you will beat Quen. You will write a paper that says, I'm smarter than Pietro. So that's kind of cool. Great question.
Yeah, the ties in general are very bad. The bounds are because there's decomposing or introducing so many variables that the bound you get is really bad.
Yeah.
But these are two types of non-complexities. You should expect very different.
Yeah. If you look at this problem here, you start off with two variables, so in a two-dimensional space, and you lift this to a nine-dimensional space. And so you can just imagine there's so much more room in 9 dimensions than there are in 2 dimensions. So just going from 2 to 3 is already much more space. So they're typically very poor. But it's general. That's the nice thing about it. Yeah. Oh yeah, over here. Yeah. Yeah. Yeah.
If you have an expression tree, with an expression tree you can write any expression and decompose it. So this reformulation code simply descends the tree, and for every intermediate node it creates a new auxiliary variable. So no matter what the tree, you can always create a reformulation with as many auxiliary variables that you have.
Yeah. So here's the tree from which you would create your additional auxiliary nodes. So each time you have a nonlinear expression there, like exponentiation, you introduce a new variable. Sine, you introduce a new variable. Multiplication, each time you do that, you introduce a new variable. And so this tree can be, you can make this as large as you want to, but it's more variables that you need to introduce. And addition and subtraction, you don't need to, because you know that the addition of two convex functions is convex. So there we don't need to do that. That's the only help that we get.